Okay, now I want to go back and look at the first problem table I asked you to solve for homework, table 5.8 on page 129. And Marisha, how many rows are there in this table?
3.
R1, R2, and R3. And how many columns?
3.
C1, C2, C3. And what are the payoffs in the first row?
7, 6, 4.
Okay, and in the second row?
3, 2, 1.
And in the third row?
5, 6, 4.
Okay, now again, let's just remind ourselves what this game table says. This is a two-person, strictly competitive game, meaning that row has the choice between 3 strategies to choose, R1, R2, and R3. Column has a choice between 3 strategies, C1, C2, C3. And what's filled in here are the outcomes for row. So if row chooses R1 and column chooses C1, row will get +7. And since it's a strictly competitive two-person game, column will lose 7. If row chooses R2 and column chooses C2, row will get a payoff of +2, column will get a payoff of -2, and so on for all of the 9 points on this particular table. Now, let's apply dominance reasoning like we did when we did table 5.9. Consider row's choice here. Notice something here. Notice that R1 for row strictly dominates R2. If column chooses C1, row does better choosing R1, 7, as opposed to 3. If column chooses C2, row does better choosing R1, 6 to 2. And if column chooses C3, row does better choosing R1, 4 to 1. Okay? So we know row, being a perfectly rational agent, will never play R2. It's strictly dominated by R1. But now look at R1 and R3 and notice something about this row. R1 strictly in C1, R1 pays off better than R3 does. +7 for row as opposed to +5. In C2, they pay off identically. It's +6 and +6. And in C3, they pay off identically, +4 and +4. Once again, R1 dominates R2, only weakly, since it pays off better in one of the columns and is identical in the other, but again, weakly dominating. We know that that row will never play R3 with R1 available. Column knows this, so column realizes that R is going to play R1, and so column is going to choose C3 in order to minimize his or her losses to -4 as opposed to -6 or -7. Here we have the dominance reaches the solution to this particular game. The solution to this game via dominance reasoning is the pair R1 C3, and the value of this game is 4 for row and -4, of course, for column. Now notice something else about this particular point. This particular point is in Nash equilibrium, right? Because if the players hit this particular point, this particular point right here, neither has any reason to unilaterally change their choice of strategies. Row has no reason to change if they get on this point, because that would be changing to either +1, which is worse than +4, or +4, which is the same as +4. Column has no reason to switch if they get on this particular point. That would be going from -4 to -6 or -7. So this particular point is in Nash equilibrium, since neither player has any reason unilaterally to change his or her choice if they hit that particular point. It's also, this particular point is also passes the minimax equilibrium test, right? This particular point right here is the minimum for row, a minimum payoff in this for row, and it is also the maximum payoff for column. And so that point it passes the minimax equilibrium test, And that point is also the security level for both row and column simultaneously. By choosing R1, the worst row can do is 4, as opposed to 1 or 4 here. And by choosing C3, the worst column is going to do is -4, as opposed to possibly doing -6 or possibly doing -7 if you choose a C2 or C1. So all of these ways of recognizing that this point right here is also in Nash equilibrium, is part of the Nash equilibrium pair.